Okay, now we're recording. Basic RL RC circuit, source-free circuit. Again, notice there is no source here. These two are connected in parallel. So if I do KCL at the top, it says the current entering that node should equal all the currents leaving that node. Well, there's nothing entering that node. We have I sub R leaving, I sub L leaving. So 0 equals, well, the current through that resistor is the voltage divided by that resistor, Ohm's law. Current through the inductor. Current. Let's see. What's the current there? Well, if you go back to, where's my cheat sheet from before? V equals L di dt, or I equals what? 1 over L, the integral V dt. I don't know where I put that sheet. I saved it last time so I can refer to it. I must have thrown away that summary. Maybe it's in the book somewhere. Well, you can check your note. You'll see we have what? 1 over L, the integral of V dt, from negative infinity to t. And anytime you have an integral, what we're going to do is actually take the derivative of that. The derivative of any constant is 0. This will be 1 over r dv dt plus 1 over L, and when you take the derivative of the integral, they cancel each other out. And if we multiply everything by r to get rid of the 1 over r in the front, you end up with what? dv dt plus r over L times v is equal to 0. And the question, how do we solve that? This is a first order differential equation. It's called differential equation because it has a derivative. And it's first order because what? It's only first degree, first derivative. So that's the first order differential equation. And the question, we need to solve it. Well, you'll learn that when you take differential equation next semester. Most of you probably signed up for differential equation next semester, right? So that's what you're going to be learning in that. How do you solve a differential equation that has first derivative in it? Notice there's no value here. And the rule is really simple. If you have, I'll just make it for any differential equation. If you have a differential equation that looks like this, I call it alpha. Usually that's a function of time, equals to 0. The solution for that is always going to be some initial condition e to the power of alpha t. I had a handout for that and I was looking for it too and I can't find it. I think it's negative alpha t. We can research that one. We can try to derive it, but I will leave it. It's negative alpha t. And if this is not a constant here, if this is the equation that looks like this, it's going to have a solution of k over alpha plus x sub 0 e to the minus alpha t. So these are actually the rules I'm going to use in solving differential equation, first order differential equation. If I have a differential equation where this is 0, there's my answer. K0 is the initial condition, some constant. We'll get to that. And if this is actually not a 0, it's k over alpha plus some initial condition e to the negative alpha t. If I compare this one to these two, it matches the first equation. So my solution for that, the voltage across the inductor, is going to be some initial condition. We'll call it V0, e to the power of negative R over L times T. So if I know a bit about the circuit, what was going on before when you had the source there, because if you never had a source in the circuit, there is no initial voltage there, so that's zero. But apparently we had something attached to the circuit initially, and that would be that value right there. That would go right here. We know what R and L, we can plug it in and go from there. Let's see if I can take an example that has some numbers in it initially. So let's take this circuit. We have an inductor. We'll put some numbers on it. And the inductor has 50 millihenry. That's the value of it. Going through a resistor of 200 ohms. And there was something attached to that circuit before. So this was attached to something else here. There's a whole circuit was driving that. But what happens at t equals to 0, we open that switch. So once you open that switch, this is no longer a factor. This is what you have left. So before this was closed, attached there, and at t equals 0, somebody came in, disconnected that power source, whatever that circuit here. So that means something was driving that. So let me give you some initial condition. Assume when this was closed, before the switch opened, the current through the inductor is 0 minus. Before we open that switch, assume that was at 2 amps. Normally we have to calculate that, but in this case, assume that was the case. The question is, find the current as a function of time. Find I sub L as a function of time, the expression for it, for t greater than 0. And I also want to find the current through the inductor at t equals 200 microsecond. How much current was going through it? Two things I'm asking for. So for t greater than 0, this is what my circuit looks like. That's it. And if there's current going through that, that would be the same current. Let's call it I sub L. Is going to mark this voltage, this inductor plus to minus, we'll call it VL, is going to mark this plus to minus, we'll call it VR. If I do KVL, sum of the voltages in a closed loop is 0. What do we have? VL plus VR is equal to what? 0. The voltage across an inductor, V equals L di dt. Plus VR, which is what? R times I. I can plug in the numbers now in it, and that will give me what? What's L? 50 millihenry? What's 50? Is that 0.05? DIL dt, because that's the current through the inductor really as a function of time if you want to, plus R, which is what? 200 times I sub L as a function of time is equal to 0. Let me divide both sides by 0.05. What is 200 divided by 0.05? 200 divided by 0.05 is 4,000, right? Now that looks like the first equation. I said if you have an equation that looks like this, a derivative here plus a constant times that function equals to 0. That's what I have. Then my solution for that, I sub L as a function of time, is going to be the current at 0 times e to the power of negative 4,000 t. Based on that equation. Now, in this problem, they stated that the current at 0 was what? 2 amp. You go, well, that's 0 minus, not 0 plus. Well, you remember anything about inductor? I sub L 0 minus equals what? I sub L 0 plus. The current does not change in 0 time. So this is equal to 2 e to the negative 4,000 t. This is for t greater than 0. That is the current through the inductor at any given time. And by the way, if you just graph that to see what it looks like, then we're going to ask you what's the current at 200 microseconds. If you graph that's an exponential function, it will look like this. At t equals to 0, what's the value of the current? 2. And what happens after that? It's going to start to decrease. It doesn't take that long to go to 0. Notice we ask you what's the current at 200 microsecond.
It's got to be close to 2.
Well, let's see. E to the negative 4,000 times 200 micro. What's 4,000 times 200 micro? That's 0.8. E to the negative 0.8. So let's do that. 2 times e to the negative 0.8. And this is what? Roughly 0.9 amp in 200 microsecond. So we're talking about a short time, actually. It's not going to take that long for that. Actually, the actual time it takes to go to 0, it's 5 over that number. 5 tau, we call that. The time to go to 0 here, we call that roughly 0 here. This is approximately 5 tau. And what's tau? That's 5 times 1 over that number, 1 over 4,000. Tau is 1 over that number. That's how long would it take for that current to go to 0. So what's 5 over 4,000? 1.25 millisecond. So that's how long it's going to take that inductor to discharge completely. Roughly 1.25 millisecond before it's no longer a factor. So we're not talking, oh, it's going to stay there for 5 seconds, 10 seconds, a minute. We're talking about milliseconds, microseconds. That inductor actually will work as a source. Starts with the value of 2 amps, start to decrease. By the time we hit 1.25 millisecond, that inductor is almost empty. All the charge is gone. Let's try a couple more examples. We'll show you what the circuit like. In this case, we gave you the initial condition. As I said, usually you're not given that initial condition. You have to find it. So here's a circuit. I have a 40 ohm resistor here. plus to minus here. Of 24 volts. There's a switch that's attached right now, but at t equals to 0, that switch opens. Swings open. There is 10 ohms, and there's an inductor of 5 Henry. And let's say I want to find this current, we'll call it I sub L. What is that current? And let's say I want to find this voltage, we'll call it V, for t greater than 0. That's what we have. The one assumption I'm going to make that this circuit been sitting like this for a while. Connected, I walked in this morning, I built that circuit, it's sitting upstairs. Been up there for at least 5-6 minutes, so you're fine. Well, if it's been sitting there for a few minutes, and since this is a DC source, how does the inductor behave to DC source? On that sheet, I summarized everything. I wish I had kept a copy of it. Maybe it's here. The inductor behaves as what? DC source, short circuit to DC source. Let me see if I have that page. I thought I saved it. I don't know where I put it. Everyone used their own, so I'm sure it's gone. So to DC, the inductor behaves as a short. That's Henry. That's not a resistor. 5 Henry. Does that look like a Henry now? It looks like a... Yep. So the inductor is going to behave as a short circuit. For t less than 0, I have to look at that circuit. This is what my circuit will look like. And this is 10. And this is 40. So I can tell you the voltage here for t less than 0 is going to be what? Isn't 24 volts? How are the three of them connected? In parallel. Well, what's the current going down here? What's I sub L? Well, that's the same current through that resistor. I sub L for 0 minus, it's been sitting there for a while, is going to be this voltage divided by that resistor. 24 divided by 10, which is what? 2.4 amps. This, and that, all connected in parallel. They have the same voltage. I'm only interested, the question, what's the current through that? So the current through that for t less than 0 is 2.4. What's the voltage here for t less than 0? That's 24 volts. Done with it. So now I have to look at the circuit for t greater than 0. So what's going to happen when t goes above 0? The switch is going to open. Once that switch is open, this source is gone. And that's what I have. That switch opens, this source not a factor. Now I'm not looking at t equals 0 plus, I'm looking in general for t greater than 0. At t equals 0 plus, that current through the inductor doesn't change. So at that instant, that current through this still 2.4. Then we'll start to shrink after that, reduce. Then we'll go to 0. So I'm looking at it for any time for t greater than 0. So I can't use the 2.4. It's only good for a microsecond. Boom, blink. It's 2.4, then start to shrink. So here's my current. This is I sub L. Is going to mark this plus to minus. It's going to mark this plus to minus. It's going to mark this plus to minus. So if I do KVL there, sum of the voltages in a closed loop is 0. Let's begin with this one. What's the voltage here? Ohm's law says 40 times I sub L. Plus, what's the voltage drop here? 10 times I sub L. Plus, V equals L di dt, in case you forgot. That's the voltage across the inductor. So the voltage there will be what? 5 times di sub L dt. All of that is equal to 0. If I simplify, I have 5 dIL dt plus what? 50 I sub L equals to 0. Divide by 5. Plus 10 I sub L. Again, that fits that equation we mentioned early. If you have a differential equation that looks like this, and that's what we have, your answer is going to be whatever the initial condition of that. So I sub L as a function of time is going to be I sub L at 0 e to the power of negative 10t. What was my initial condition for the current? 2.4. E to the power of negative 10t for t greater than 0. That is the current as a function of time. Notice at t equals to 0, if you plug it in, when t is 0, what's e to the 0? 1, what do you get? 2.4. We said the current at t minus and t plus are the same. So 0 minus 0 plus, your current is the same, 2.4. So if you were monitoring what the current looks like, again, the current through that inductor, it was a 2.4 for t less than 0. That's the 2.4 right here. I don't know if you can see the 4. That's 2.4. Then what happens after that, it goes from 2.4 like this. How long is it going to take for this to be 0? Well, let's see. It's 5 tau. So that's 5. Tau is 1 over 10. You're right. That will take half a second before that current, that inductor, has no more charges left in it. So half a second. And after that, the voltage or the current through that will be almost a 0. Again, the point I'm trying to make, it's not a long time. It's a very short time. You want to find the voltage now? Well, if you remember, the voltage was labeled in the problem where? Plus on the top, minus on the bottom, right? The way the current going is going to label it what? Plus, minus. So what is V going to be? The voltage across the resistor is going to be negative 40 times I sub L. So that's negative 40 times 2.4 e to the power of negative 10t.
Where is the negative 40 coming from?
I'll put that in a second. because the voltage was labeled, they wanted V plus on the top, minus on the bottom, right? And notice the way the current is going in this circuit, the current traveling which way? This way is going to mark it plus to minus, and they want the plus to be here, the minus down. So you can see these guys are backward. That's where the minus comes in. So it's negative 96 e to the power of negative 10t.
You can do the same thing for the other resistance.
Sure. If you want to find that volt, it'll be 10 times I sub L. If they want it this way, plus and minus. So notice first we have to look at the circuit for t less than 0 and calculate. If you have an inductor, you want to find the current through the inductor as 0 minus. If you have a capacitor, you want to find the voltage across the capacitor as 0 minus, not the current. Because for a capacitor, the voltage of the capacitor is 0 minus, the same as 0 plus. So let me take one with the capacitor here. Here's my circuit. I have a 2 ohm resistor on the left side. We have a voltage source very similar to the previous one, but 9 volts here. And is attached, is connected at t equals to 0 swings open. I got a 4 here. And I got a capacitor with the value of 10 microfarad. And the question, what is the voltage across the capacitor? That's what I'm looking for. Find V sub t, the voltage across the capacitor at any given time. Now again, we have to look at the circuit for t less than 0, and I need to find the voltage across the capacitor as 0 minus, because that's the same as the voltage across the capacitor as 0 plus. So when you have a capacitor, you don't want to find the current, you want the voltage. When you have an inductor, you want to find the current through the inductor, because that doesn't change. So again, assuming it's been sitting there for a while, how does the capacitor behave to a DC source?
Well, if we short an inductor, isn't this one open?
Yes, that'll be an open. And what's that voltage equal to? Looking at that circuit, what is it?
0.
No, 0, that was a short circuit. 9 volts. Why 9? If this is ground, what's this voltage here? 9 volts. How much current go in that direction? None, 0. So the voltage drop here, Ohm's law says V equals I times R. 4 times 0, which is what? 0 voltage drop here. So that end is going to be the same as this, 9 volts. So that's all I need. What is the voltage across the capacitor? 0 minus. That's 9 volts. That's the whole purpose of looking at the circuit for t less than 0. Now, let's look at it for t greater than 0. For t greater than 0, the switch is going to open, and my circuit will look like this. Now you can combine these two if you want these two resistors. And that would be what? 6, 10 microfarad. Now again, if I do KCL at the top, this is I of R coming down. This is I sub C coming down. I define them. I do KCL at the top, which says sum of the currents entering that node equals sum of the current leaving that node. What is entering that node? Bless you. 0. What's leaving that node? IR plus IC. I is the voltage here, which happens to be the voltage across the capacitor, divided by 6. And if you remember, for capacitors, I equals C dVc dt. So that would be 10 micro dVc dt. Let's divide by 10 micro. So dVc dt, that's 1 over 6 divided by 10 micro. 1 divided by 6 divided by 10 micro. Where's that EE? Where'd you go? Here we go. I got 16667 roughly. VC equals to 0. 16,667. Or 1 over 6 micro if you want to, if you don't like that number. So if you don't like that number, plus, if you don't like that stupid number, you can say 1 over 6 times 10, 60 micro. That's what that number is, 1 over 60 micro. Does that look like a 60? Yeah. So if you go 1 divided by 60 micro, 1 divided by 60 e to the negative 6, notice the same number. I don't know if you can see it. Gotta find the spot. 1 over 60 micro is the same number. So if you don't like to use that number, you can use this number. So this is your alpha. So what's the voltage across the capacitor? Because that fits that equation there. The voltage across the capacitor at any given time is, the voltage across the capacitor is 0, e to the power of negative this one times t. So if you don't want to use 16,667, you can use that one. And what's my voltage across the capacitor? Isn't that 9? E to the negative 1 over 60 micro times t. That is the voltage across the capacitor at any given time. What was my question for that one? Find the voltage? Yep. That's it. If they ask you for the current, what would you do? If they say, what's the current through the capacitor? Well, the current is what? C, which we know what C, 10 micro, times the derivative of that. So if you want the current through the capacitor, what is C? 10 micro. Let's see how good are you in calculus. What's the derivative of this? There's the 9. What's the derivative e to the minus 1 over 60 micro t?
Times 1 over 60.
Negative 1 over 60 micro. E to the what? Negative 1 over 60 micro t, right? And if you do the math, the micro and the 0 will cancel here. That'll be a 6. That's what?
90 over 6.
Negative 9 over 6, because 10 cancels the 0, cancels the 0, right? The micro will cancel the micro. The 10 cancels the 10, the 0 here. So 9 times the negative 1, negative 9 over 6, which was what, 3 over 2? E to the power of negative 1 over 60 micro times t, for t greater than 0. That's the current through the capacitor at any given time. So once you know what the voltage is, you can find everything else. You can find the current. Do they want to know what the voltage right here is? 4 times I. Do they want the voltage here? 2 times I. You can multiply them through. Get everything that you need. Let's try one more example, maybe make it a little bit bigger here, and take advantage of everything that we learn. Here's my circuit. 120 ohms, 60 ohms, we have a switch here, plus to minus 18 volts. The switch was connected, then swings open at t equals to 0. $90 ohms here. 1 millihenry inductor here. Another 50 ohm resistor here. Another inductor here of 2 millihenry. And finally one more inductor right there of what? 3 millihenry. It's really not a big deal because you can combine a lot of these. And the question for that is, can you tell me what the current through this, I sub L, as a function of time? That's what we're looking for. Find I sub L.
Inductors are combined when...
Correct, we can combine just like resistors, the product over the sum here. But if I look at this for t less than 0, and again, I'm assuming it's been sitting there for a while. My source is right here. That's 18. This is the 9. This is what now? Short circuit? Inductor is always a short circuit. There's 50. Short circuit. Short circuit. This is I sub L. And there's one, well, there's 102 resistors. Combined together, that's what, 180? And where are they connected?
Parallel with the...
With the source and the 90. Yep. Notice, it's really right there, attached, and it's right here, the same point, right? This is all one node. So that 180 is actually here if you want to. You can put it up there, big deal. But that's the same thing as connect them right there. So if you clean that circuit a little bit, this is what you're going to have. 18. These two resistors combine into one. The product over the sum.
And then you can do the one in series with 50.
90 times 180. Now I'm going to leave it at because I'm looking for that current. Over the sum of them, what's 90 and 180? Is that 270? That's a 60. And that's the 50. And I'm looking for that current, I sub L. So I sub L at 0 minus, which is the same as I sub L at 0 plus. Notice this, and this are connected how? Parallel. They have the same voltage. The voltage is 18, the resistor is 50, so the current's 18 over 50, which is what? 0.36 amp. That is the current through I sub L for 0 minus. You can move that resistor and put it right there. You'll see they are in parallel. All three of them are in parallel. So I got what I need out of it for t less than 0. Now I got to look at it for t greater than 0. This switch opens, which means that source is gone. So if that source is gone, here's my circuit for t greater than 0. I have the 90 right here. There's that 180 right here. There's that inductor there, it's not gone, 1 millihenry. There's the 50. And I can take these two inductors, combine them together to make it what? The product over the sum. 2 times 3, 6. 6 divided by 5, what's that, 1.2? Product over the sum. This is I sub L. I can take these two resistors and make them one, which would be what, 60?
Yep.
You can combine them even more. 60 and 50, which is what? 110. The inductor will be what? 2.2 millihenry. By combining them, does that change the current through this one? It's the same current. So I can combine them without affecting the current. Now that's my circuit. I can do a KVL here. Sum of the voltage in a closed loop is 0. So the current's going this way, So V equals L di dt plus R times I equals to 0. L is what? 2.2 milli DIL dt plus R, which is 110, I sub L equals to 0. What is 110 divided by 2.2 millihenry? 50,000. So now I know the current through the inductor. I sub L as a function of time for t greater than 0 is going to be I sub 0 e to the power of negative 50,000 t. Do we know what I sub 0 was? Wasn't it 0.36? Again, if I was to graph that current through that inductor for t less than 0 was 0.36. So for t less than 0, after you set for a few seconds and let it sit there, you built it last month, the first 2 seconds I'm not looking at it, after that it's set like this, 0.36. You walk into the lab, you disconnect it, it's going to discharge.
What happens when you first turn it on?
It's the same thing, it's going to charge just like this.
Okay, so it's at the opposite?
Yep. So now, this is 5 tau. And that's 5, and tau is what? 1 over 50,000. What's that? 0.1 millisecond? So that's how long that capacitor or inductor is going to behave as a source for just only 0.1 millisecond. Then after that, the whole circuit, psh, gone.
I think it's 0.01 actually.
1 over 10, right? That's 5 over 50, that's 1/10, and that's a milli. 0.1 millisecond. I think I'm right. 5 divided by 50,000. Yep, 0.1 millisecond. So that's how long again that's as a source there. Again, we can make the problems bigger, add more stuff to them. Now, instead of using switches, a lot of times we walk away from this, we start using unit step function. So instead of a switch, remember with the switch, it looks like this. If you have a source that looks like this, let's say this is 5 volts, and close at t equals to 0. For t less than 0, what's the value of that? Nothing. It's open, right? So this one kicks in when t equals to what? 0. Do you know what unit step function looks like, the graph of it? The graph of u sub t is called unit step function, has a value of 0 for t less than 0. Then it goes to 1 at t equals to 0. That's a unit step function called u sub t. I don't know if you saw that in math or not. So instead of using a switches there, we go, you know what? My source here is 5 u sub t. That's the same as that one. Because for t less than 0, this is open, it's no big deal. For t less than 0, what's the value of that source? 0. 0 times 5? Nothing. What happens at t equals 0? This one closes, and what do you have now? 5 volts? What happens when t equals to 0? U sub t has a value of 1. 1 times 5, which is what? 5 volts. So instead of using switches, because people don't want to draw the switches, you'll see us actually use u sub t to replace the switch. And I'm going to do that next time, next video, on Thursday. I'll stop here, but that's just what's coming up next. Instead of doing switches and all that, we're going to look at u sub t.